is SciTime.
It's SciTime for grade 6 to 11 students. Today I brought you a digital science lesson. First I'll explain how to use this science lesson. Step 1. You must download this questionnaire from the link below. Step 2. Pause the video and read the questions well. Step 3. Play the video back and find the answers to the questions while watching the video. See what I have brought to you. It's an ordinary ball, a plastic ball. So we know we can play with balls. But today we will learn kind of science fact from this ball. See what we can learn from a ball. I place this ball at rest on the desk. Now I am giving challenge to you or ask you to do something. If you have a ball in front of you like this, can you move this ball? Somehow can you move it? If I add something, without touching, can you move the ball? Without contacting the ball. So let's try to do kind of thing like a magic here. So I'll keep the ball here and slowly try to lift it up with a kind of magic event here. And you know that's not a magic. Every magic is a science. So what's the science behind that magic? There was a thread, small thread attached to this ball in hidden way. Let's explain the science behind this one. So I have tied a thread to the ball. When I pull the thread up, the ball follows it because this thread tied to the ball and it gives a pull to the ball, just pulling the ball up. Such pull is called as a force. So today we will learn about forces, many things. So pull is a force, and not only that, if I can give push to the ball, that also a force. Simply in early grades we define the force as a push or a pull. Here, this ball we moved by giving force push or pull. There are two methods that we can give push or a pull. One thing, if I attach that thread again to this ball, you can see here. Then one thing, by the thread we can pull it. There is a force created by this thread. It is called as tension force. When we pull a rubber band, the tension comes. So one type of force is tension force. And also we can move this ball by giving impact. That force is impact force. Both these impact force and tension force are called as contact forces because we need to contact the object to do that. Can we move something without contact? Not by something like the previous magic. So let's take an example. I will keep the ball here on a stand. This stand here, I will keep the ball here on this stand. So you can see the ball is rested at the stand. Is there any force acting on this ball now? It's at rest. Actually there is a force. That force is the pulling force by the earth. If I remove this, ball pull down. And was there any contact of this ball and the earth? No, there is no contact. But earth can pull it. You know that pulling force is the gravity, also called as gravitational force. It's a non-contact force. Right. Are there any other non-contact forces? Let's try another simple activity. This is also a familiar one to you. I will take this one here. Let's keep the standard here. Right. This one. This is the black plate here. I will take a piece of paper. And there's a piece of paper. I will tear those papers into small pieces. Tear it up. Few pieces of papers I am taking. Then I have a plastic rod and a sponge. First, let's rub this one with rubbing it. And this time we are not going to contact the papers, but you can see the papers jump up. Papers attached to this without contact. Such non-contact forces are known as electrostatic forces. So gravity and electrostatic force are non-contact forces. Can you suggest another non-contact force? This time I will take a nail. Can you move this nail without contacting the nail? Sure, we can do it, but you need a magnet. So let's keep it. Yeah, I took that to a magnet. So magnetic force also a kind of non-contact force. And force types. Forces, we can divide forces into two types as contact forces and non-contact forces. Contact forces are two types: tension force, impact force. Non-contact forces, they are three types: one, gravity, gravitational force; electrostatic force; and magnetic force. Let's see what a force can do. This time I will take a rubber ball. Let's keep the ball here at rest. Then, this time I'm going to apply force here, giving a force. So we saw that ball is moving. A force can move a rested object. First thing that a force do. Second thing, ball is now slowly moving and applying force again. To the same direction I am applying the force. Ball is moving and applying the force. So ball increases its speed. Force can increase the speed of an object. Second thing. Number 3, ball is moving and I just slow it down. Again, ball moving and slow it down. Force can slow down or decelerate the motion. Next thing, ball moving this way and giving force to the other side. Again, moving and giving force. It's changed the direction. So a force can change the direction of a moving object. And what else? Still ball is moving and I stop the ball with the force. Moving object we can stop with the force. So 5 things we can do by means of motion by applying force on an object. Again, by applying a force we can do 5 things by means of motion. First thing, moving a rested object. Accelerating, speeding up a moving object. Slowing down a moving object. Changing the direction of a moving object. And stopping a moving object. Are there anything else that force can do without moving things? Let's see this. Still I have the rubber ball in my hand. if I squeeze it, you can see the ball change its shape. So a force can change the shape of an object. Next, I'll take rubber band. This rubber band, if I pull the rubber band, its length increase. A force can change the length of an object. And I have wooden stick here. So this time if I give force to this, you can see it break into parts. So force can do something else other than motions on the objects. First, changing the shape of an object, changing the length of an object, breaking an object into parts, or shattering an object into parts. That's what force can do. This time, a scientist thought how to measure this force, or how to find the magnitude or the size of a force. Look at this. Again the rubber band. If we hang something here, the rubber band increase its length. So that was the theory used by the scientist when making a force meter. Here I have a force meter. Let me show that. Look at this. This is the force meter. We call this as spring balance or Newton balance. Why do we call this as Newton's balance? To find more facts, we can go to today's facts from the Wikipedia. Let's see this.
Sir Isaac Newton, born in 25th December 1642, was an English mathematician, physicist, astronomer, and author who is widely recognized as one of the most influential scientists of all time and as a key figure in the scientific revolution. Newton himself often told the story that he was inspired to formulate his theory of gravitation by watching the fall of an apple from a tree. Sir Isaac Newton, walking in his gardens, had the first thought of his system of gravitation upon seeing an apple falling from a tree. He questioned, why should that apple always descend perpendicular to the ground? Why should it not go sideways or upwards, but constantly to the earth's center? Assuredly, the reason is that the earth draws it. There must be a drawing power in matter. The sum of the drawing power in the matter of the earth must be in the earth's center, not in any side of the earth. Therefore, this apple falling perpendicularly or towards the center, if matter draws matter, it must be proportion of its quantity. It must be a force. Then Newton formulated three statements on force. Newton's laws of motion are three physical laws that together laid the foundation for classical mechanics. They describe the relationship between a body and the force acting upon it, and its motion in response of those forces. More precisely, the first law defines the force quantitatively. The second law offers a quantitative measure of the force, and the third asserts that a single isolated force doesn't exist. The Newton symbolized by capital N letter, is the international system of units derived the unit of force. It is named after Isaac Newton in recognition of his work on classical mechanics, especially Newton's second law of motion. We took this article from Wikipedia and it says, why do we use Newtons to measure the force? It is just to respect Sir Isaac Newton.
How to use this Newton's balance and what is the principle of working this balance? So let me arrange small stuff here. Let's take this stand and keep it here. Let's keep it in this way. That's better then. Okay. And let's hang this spring balance like that. Now you can see there is a spring here. When I give a force, the spring stretch. So from the box here, you can see zoom view, more clear view. When I pull this down, it increases the length. And what is the unit of measuring force? Let's find it out. If you see the reading here, look at the corner, and you can see it's marked as N letter. N stands for newtons. Now you know why do we use the unit newtons. And we can see two sides in this spring balance. The other side you can see it's marked as G, stand for the grams, and one side is grams, other side that is newtons. Let's compare a gram value to the Newton value, or the weight and the mass. Today's activity is finding the magnitude or the size of the force. To do this activity, we need three things. One, a force meter or spring balance, and a weight set. To keep or to hang this spring balance, we need stand. Let's do the activity. We stand on the earth. Always there is a pull by the earth. That pull creates kind of force called gravitational force. Force on an object we can measure by this. So let's take this one. I have few weights here. Let's take one weight from that. Only one weight. Let's keep the weight here and hang this one. And let's see the reading again. Here you can see the reading. It's 0. No, this side is grams. It is 50 grams. And what is the force created by the gravity? You can see it in the other side. That is 0.5 newtons. 50 grams is the mass and 0.5 newtons is the weight. Let's put one more weight like this, and see the reading now. It's 100 grams and the weight in newtons, that is 1 newton. 100 grams on earth is equal to 1 newton of force or the 1 newton of weight. And next I will put one more. This time the weight is 1.5 newtons. Guess the gram value. See that? it's 150 grams. So there's a relationship between these grams and the newtons, because we are doing this experiment on Earth. The Earth pull is constant throughout our experiment. So by including these ones, we can fill this table here. One side you can see the grams and the newtons. 50 grams, 0.5 newtons. 100 grams, 1 newton. 150 grams, 1.5 newtons.